Good afternoon, everyone. My name is Wang Zhu. I'm from China, and I study in Kyungshan National University. Thanks for attending my presentation. My report is characterization of adsorptive PEI PVC, electrospun nanofiber membrane, and its application. Here are the contents. The plastics are widely used in our daily life due to their outstanding properties, but along with their widespread application, a large amount of plastic waste are generated every year. It is estimated that from 1950 to 2015, about 8.3 billion metric tons of plastics have been produced, and among them, about 70% became the plastic waste. All the various methods, including the physical methods, thermal or chemical treatment, and the biological methods, have been developed for plastic waste treatment, but most of these methods are not suitable for large-scale application because of the low efficiency or high energy demand. So, landfilling and incineration are still the main methods for waste plastic disposal, but landfilling occupies a large amount of limited land resources, and the incineration of plastics, especially PVC plastic, can generate dioxin, the most toxic and carcinogenic byproducts. Among various plastic waste, the recycling rate of PVC is extremely low, and PVC cannot decompose even under perfect conditions. So, considering this situation, the incineration and landfilling also not good method for PVC waste disposal. So there is an urgent need to develop new methods for PVC waste management. The textile industry is important for modern society, but along with the textile process, a large amount of dye wastewater is generated. The release of dye wastewater into the environment not only harmful to the ecosystem, but also pose great threat to the human health. So the removal of dye from wastewater before discharge into the water body is also very important. So in this study, we propose a simple method to convert PVC into unfunctionalized PVC membrane and apply it for dye wastewater treatment. The membrane was prepared by the following method. First of all, the PVC and PI solution were prepared by dissolving PVC and PI in DMS ketchup solution, and then the solution was mixed at the ratio of 2:1 and heated under 80 degrees Celsius for 4 hours to obtain the PEI cross-linked PVC solution. After cooling to room temperature, the solution was used for electrospinning to get the PEI PVC membrane. Here are the conditions. Various techniques were used to analyze the membrane. Here is the FTR analysis result. As we compare the FTR threshold of PVC and PI PVC, we can see the new peaks corresponding to amine groups appear in the FTR threshold of PI PVC membrane. This indicates that the PEI and PVC was well crossing with each other. And here is the same analysis result. Figure A and B are the same image of PVC membrane and the PI PVC membrane. And C and D are the histograms of the distribution of the nanofiber diameter of PVC membrane and the PI PVC membrane. As we can see, the PVC membrane was loose and the average fiber diameter was about 713 nanometer. But after crossing with PEI, the fiber was more compact and the fiber diameter decreased to 181 nanometer. This was due to the cross-linking with PEI increased the polarity of the solution. So during the electrospinning process, the fiber became more thin. And here is the TGA analysis result. As we can see, the decomposition of the PVC membrane and the PIPC membrane shows the 2-stage and the 3-stage respectively. And for PVC membrane, the first stage is the dehydrochlorination of the PVC molecular chain. And the second stage is the copper bond breakage, the cyclization, the formation of aromatic compounds, and so on. And for the PIPC membrane, this is the first stage, but ahead of the first stage, here is a slight weight loss, which was the evaporation of the water molecule. Because here is many amine group on the membrane surface, so it's very easy to absorb some water molecule. So the first stage is the decomposition of the amine groups and the gradual depolymerization of the PVC. And the second stage is the further dehydrochlorination of PVC. And the last stage is the degradation of PVC and the PI backbones. As we can see here, after cross-linking with the PEI, the decomposition temperature decreased from about 250 degrees Celsius to about 150 degrees Celsius. But even the thermal stability of the membrane was decreased, this membrane is still capable for high temperature dye waste treatment because the water temperature cannot reach over 100 degrees Celsius. Here is the water contact angle analysis. As we can see, the membrane, the PVC membrane is hydrophobic and with an water contact angle of 132.5 degrees. On the contrary, the water contact angle of the PEI PVC membrane decreased from 112 degrees to about 9 degrees within 16 seconds, indicating it's a hydrophilic membrane. After cross-linking with PEI, a large amount of amine group were introduced on the membrane surface, so convert the membrane from hydrophobic to hydrophilic. Mechanical strength is important for a membrane because they are operated under pressure. The membrane the mechanical strength was analyzed for 3 times, and the average result is here. As we compare the average stress and the strain of the PIPC membrane to 2 commercial membranes, this is the PP membrane and the PTFE membrane. As you can see, the stress of PIPC membrane is higher than this membrane, but a little lower than this one. But the strain of our PIPC membrane is higher than these 2 commercial membranes. This indicates is a good mechanical strength, and therefore the PIPC membrane has a good potential for industrial application. Here is the theta potential analysis result. As we can see, the potential of the PVC membrane was 3. The pH point of zero charge of the PVC membrane was 3.1, but the pH point of the PIPC membrane was 10.8. This was due to the cross-linking with the PEI. A high pH point of zero charge indicates that at the pH below 10.8, the surface of PIPC membrane was positively charged. This is favorable for anionic dye removal in a wide range of pH. And we use a self-made dead-end filtration system to analyze the dynamic absorption separation performance of the PIPC membrane. The effective surface effective area is 8.55 centimeter square, and the pressure is 1 bar. We analyze the pure water flux, and the result is about 3013 plus or minus 60 liters per meter square per hour under 1 bar. video shows the filtration separation of dye from by the membrane. As you can see, the the colored water, dye water, was quickly purified by this membrane, which is very interesting for industrial application. We also investigated the pH effect on the separation performance of the membrane for reactive dye. In the pH rating of 4 to 9, as we can see, with the pH increase from 4 to 9, the breakthrough point appeared in the filtration of 1,690, 1,050, 6,690, and 185 milliliter of dye solution, with a rejection rate over 95%. This result shows that in the pH range of 4 to 8, this membrane can purify a large amount of dye wastewater. So it's a very it's a good performance for the real application. We compare the removal efficiency performance with other membranes, and we can see the PEIPC membrane have a relatively high rejection rate for reactive dye, even under high water flux and low pressure. The reusability of the membrane was also investigated. Here is the result. As we can see, after 3 cycles, the removal efficiency of the membrane was only slightly decreased, indicating its good usability performance. Therefore, in conclusion, in this study, an adsorptive PEIPC membrane with excellent property for dye wastewater treatment was successfully prepared by natural spinning. The membrane was uniform, heat-free, with a highly porous structure and good mechanical strength. It could be applied to high-temperature wastewater treatment, and the membrane was hydrophilic, and the mean pure water permeability was 3,013 plus or minus 60 liter per meter square per hour per bar. The membrane could purify a large amount of dye wastewater over a wide range of pH 4 to 8, and the membrane has good reusability for reactive dye wastewater treatment. That's all. Thanks for your attention.
좋은 발표 감사합니다. 혹시 질문 있으신 분 있으시면 손 들고 질문해 주시면 좋겠습니다. 없으신가요? I have one small question. You have shown us the water contact angle change during very short time. What does the time mean? Is that the reaction time or fabrication time? What does the time mean?
This when we analyze the water contact angle, one drop of water was put on the membrane, and within 16 seconds, the water drop quickly penetrates from the membrane.
Is it the time for the measurement?
네.
네, 그러면 질문 더 없으시면 다음 발표로 넘어가도록 하겠습니다.
네, 감사합니다.